We're live, I think. Let's assume so. So we're in the 10:30 section, lecture number 7, Fourier Series, and maybe I'll even get to Fourier transforms this time. I promised you that last time. I really didn't come close to that. So thanks for coming back and sticking with me, and we'll get there. There's actually. Depends on what I feel like talking about for Fourier series, how much Fourier transforms we do now versus after lunch. But let me sort of go through quickly what we did last time with Fourier series. We started off by reviewing the orthogonality of sines and cosines. We use those orthogonalities to find out the coefficients of a Fourier series. And my first example was a trigonometric Fourier series, where I take an f of t that's periodic, and I expand it in terms of a sum of cosines and a sum of sines, with magical coefficients a's and b's, that basically tell you how much of each of these harmonics you have. So if A27 is bigger than A2, you have more energy or more signal in the 27th harmonic than you do in the second harmonic of that cosine. So these indices, and I can talk about this now that we've done an example or two, these indices actually give you another graphical representation or table representation. You can draw your function in the continuous time domain, or what you can do is you could have a table where you have A's and B's and what the value is for A1, for A0, A1, A2, A3, A4, B1, B2, B0, B3, B4, and so on. And if you want to, you could probably figure out a way to plot those in a discrete time case. A discrete frequency space. So the K or the ends here, the ends of the harmonic, actually is a discrete index that relates. So we've moved from a time domain continuous function to a discrete frequency representation of that information. So continuous in time, discrete in frequency. Okay. So maybe what I should do is I should scribble that onto the notes. Well, doesn't really matter. And then we use orthogonality to find out what A naught is, and all the A's, and all the B's. Okay. And there are some nice physical interpretations. For example, of the A naught, that's the average value of the function. So, if you take it, we'll go through our square pulse, our rectangular pulse. The average value of that is the DC level of it. Okay. In addition to the trigonometric, there's also the complex exponential notation, the complex notation. The A's, the distinction between an A and a B is how much is in phase and how much is out of phase, and I'll slip in a term of art called quadrature. In phase quadrature, cosine, sine. Okay, I'll say more about that later on. But those relative phases are now kept track of with the J's. And one thing I didn't do here, but you might want to think about, is what is the relationship? What is the precise relationship between alpha sub k, A, and B? What is the precise relationship between alpha sub k, A, and B? In other words, if you go through and you calculate alpha sub k's, can you quickly and instantaneously get the A and the B for that k? So you might want to think about that and see if you can come up with a formula for that. Okay. What if it's not periodic? Well, if it's not periodic, you make it periodic. You force it to be periodic, and you force it to be periodic with a period longer than what you're interested in. And so you say you're interested in a particular time, and by golly, you hold yourself to that. You make it periodic outside of that. A couple examples. The example we were working on when we quit last time was a rectangular pulse, and we were working through the exponential Fourier series. So we have a rectangular pulse. The width of that pulse is 2t1, and it's centered on the axis to make it a nice even function. We said it was periodic with a period of capital T naught. So every T naught, the pulse repeats. Every capital T naught, the pulse repeats. The average or length of time that this is on, above the axis, is the alpha sub 0, and we also call that the duty cycle. Okay? So the formula for alpha sub 0 gives rise to a physical interpretation of the average amount of time that the pulse is on, which in the term of art there is called the duty cycle. Okay? The rest of the formula, the rest of the alphas are calculated by straightforward integration. It's a simple integral to do because the pulse is simple. It has definite limits where the pulse exists, where it's 1. A few identities gets us a reasonably simple expression for all the alphas. For all the alphas. And what we were doing before we were so rudely interrupted by the end of the camera. No worries. We were starting to look at some cases. So we did the case of T0 is equal to 4T1. And we simplified our alpha sub k for this specific case. And we saw that it was a discrete function in k. K is in the index. It's k space. And that's a shorthand for k omega naught, which is a frequency space. So this is k, but it's a conjugate space for time. And you'll see that because our function is even, all our alphas are real. That's a very special case. All our alphas are real, and that makes the reason I'm happy about that is it makes the plotting very trivial. It makes the graphical representation or the tabular representation of that very trivial. If I had an A and a B, if I had a real part and an imaginary part, I'd probably have to do something like square the A's, square the B's, add them together and square root them. Which is fine, you can do that, but it's kind of a headache. And then that would give me the magnitude, but it wouldn't give me the phase, and so I'd have to have a separate plot for that. And well, it's just cleaner to have that parity and revel in the simplicity of the plot. Okay, professor's prerogative. The small shifted case is a great test question or homework question or what have you. When I put 4T1 in here, the T-zots cancel, and I'm left with this. And so I record the values of each and every alpha sub k by looking at K0, K1, K2, K3, K4, K5, and I get a plot that looks something like this. Fairly tight relative to that because T naught is a little bit longer than the pulse, about twice the length of the pulse. I think I said the pulse was twice T1. Is that correct?
That would mean like 50% duty cycle?
That's what I'm getting at. That's 2 times 2T1. And I want to make sure of this. Sure, 2T1 is the length of the pulse. And so that's a duty cycle of 50%. So that's 2 times 2T1. Okay, so that's a fairly relaxed, it's a fairly good starting point for that. It's a fairly long pulse. Okay, 50% duty cycle, and so most of the energy is clustered in close to the axis, low harmonics. Okay. I will point out, and I don't know if I noticed this. You mentioned that it was related. It looked like a sinc function, a sine x over x function. And I don't disagree with you, except one of the things that I wanted to point out is this is a discrete time sinc function. It's a discrete, not discrete time, it's a discrete space sinc function. So it's not a continuous function. It only exists at certain integer values of k. So this is a discrete, I'll write time, but then I'll cross it out function. Okay? So we've continuous time function using the Fourier series gives me a discrete representation in the frequency space. Just a quick couple of extra cases. So I'll do a shorter pulse. I'll do a lower duty cycle, which means a shorter pulse. If I'm compressing it in the time domain, what do I have to do in the frequency domain? Spread it out. Spread it out. So let's see. Who knows? Maybe this will actually work. So my alpha sub k's. Instead of a pi over 2, I have a pi over 4, which looks to me like a faster behavior, or rather a slower behavior. So the sine of 0 over 0 is still 1. My first 0 is going to occur when k equals 4. 1, 2, 3, 4. Minus 1, minus 2, minus 3, minus 4. And so it just takes a little while for this function to come down to 0. My next 0 is going to be at 8. 1, 5, 6, 7, 8. And it's going to spend some time under the axis there. And similarly, 5, 6, 7, 8. Under the axis there. So I've got the wiggling going on. I've got the wiggling going on in the numerator, and I've got the 1 over k roll off in the denominator, very similar to the sinc function. These are crummy plots. I'm not even labeling my vertical axis. So I know that you're just dying for the lunch hour and this evening, so you can go home and plot this up in Excel in a much more careful manner. And I apologize for making you wait those 12 hours to do that. But you know, just bear with me. It'll all be okay. Okay. I don't know how much. I don't know. In our signals and systems courses, how much did you work with sequences or discrete functions? For example, discrete time functions. Did you guys, for example, solve a difference equation by substituting in a discrete exponential?
No, we barely touched on difference equations. We just did low pass using difference equations, just waiting the delay.
Okay.
And that was the extent.
Okay. Well, what I'll point, maybe other sections were different. I don't know. But that doesn't surprise me. It's not hard. You can see from just this plotting, it's not hard. It's just a stream of numbers. Plotting this in Excel is about the simplest thing you can think of because you just have a column of k's and a function of those k's, and the k's happen to be integers. But it is interesting to note that I can take a first difference of this, and so on and so forth. So there's a whole set of mathematics that rolls around with these discrete functions, discrete time, in this case discrete frequencies, and they're used. I'm not saying that you should rush right out and learn all that stuff, but you should know that it's there in case it helps you through a project or two in your future. Okay. You might be much more experienced at those, I think, than probably even me, right? Math major as an undergrad, great major. Let's just to belabor the point. I'll make my period much longer than my pulse. So now my pulse is much narrower than the free cycle. My duty cycle is much lower, much smaller. So my pulse is even smaller still, which means my frequency is going to be spread out even more. The alpha sub k, and I'm skipping a step which you might want to fill in, which going from the general case of alpha sub k to what the final answer is. The denominator stays the same as it did before, but the sinusoids, or the wiggles on it, That's a very precise term. I apologize for that. But the wiggles on it are much slower. The first 0 is at k equals 8. 1, 2, 3, 4, 5, 6, 7, 8. And again, I'll be real sloppy because I know you guys are going to go into that almost looks the same. And it's the same on both sides, and it goes negative there. And so it's much wider in the frequency space. Okay.
So these like more accurate than the other ones?
No, I'm sorry. Let's go through the three cases to put them in context. It's a great question, and I apologize for that. We have the general case. Okay? And the general case demands a ratio of 2 pi over T naught over T1. So in here is a 2 pi over T naught times a T1. So what I have to do is I have to put in, and I'll remember the K in there just so we don't get confused. So I have the 2 T1 over T naught. That's the duty cycle, right? So I'm doing different duty cycles. I'm doing a 50% duty cycle here, and I get this guy here. I'm getting I do a 25% duty cycle here, and it spreads out some more. So this is a different case than what I did before. And then this is a 12.5% duty cycle. Okay? So they're all sloppy. They're all inaccurate, but they're different cases. How's that for an answer? Okay? I'm going to file all those notes with Lecture 6 because that's sort of where they belong. All right. I'm going to do something that's a little bit more obtuse than I usually include, but I kind of want to do it. I think this is predicated on one of your comments that you didn't you may not have done a lot on the Fourier series in your signals and systems. And so there's one thing about motivation for the Fourier series that I hope you've seen, and maybe if you haven't seen it, it's kind of good to see. And I mentioned early on that one way to get comfortable with this, a very weird way to get comfortable with this, is to say, okay, I have f of t, and I can write a Taylor series for that. So I can write that as an infinite polynomial. And then the cosines have infinite polynomials, and the sines have infinite polynomials. And so what I can do is I can match up the 0th polynomial here with the 0th polynomial here with the first polynomial, the second polynomial, and so on back and forth. So I can equate those terms, and I can rewrite all of these as just a Taylor series is equal to some Taylor series with structure on it. Okay, and so that's all well and good. And that gets you comfortable with this, but then you're left with the nagging doubt: is why the heck do I care about a Fourier series? Why do I care about doing this in the sines and cosines instead of just Taylor series? Okay, and so one of the answers to that has to do with how good an approximation the Taylor series would be to a Fourier series. Okay, now if I keep infinite terms, I don't have to worry about the word approximation. But I'm sorry, we're not. When we employ Fourier series, we're never going to keep infinite terms. Okay? Even the example where I got a closed form solution for all the alpha sub k's, you'll notice that I only plotted them for a dozen or so spikes. There's no way I went out to infinity. I just scribbled down some lines until I got bored, which was about 12 to 15 lines, and then I called it quits and went home, figuratively speaking. So the question is, so the issue is, you're always going to truncate a Taylor series, and you're always going to truncate a Fourier series because we don't have time for infinities in this lifetime. Okay? How's that for metaphysical? So, there's something about the Fourier series that are kind of special, and the special thing about it has to do with something called a mean square error. A mean square error. And so, if I have a function, and I'll confuse you and I'll call it f of x instead of f of t. And I have an approximation to this function. And I'll call this g of x. Then there's a little space on this side here and a little space on this side here for which the g of x and the f of x don't quite match. Okay? And so what I could do, if I wanted to put a fast foot over on you, is I could say, well, I'm a little low here, but I'm a little high here, and they cancel out, and all's well in the world. But you shouldn't tolerate that, because that would also mean that this red line could be really far off, and the errors, the linear errors would cancel, and you wouldn't have any insight onto how good a fit it was. So the answer is to look at the energy of the error. The answer is to look at the energy of the error. So you square this part here, and you square this part here, and then all of a sudden the fact that the red line is lower than the blue line here, and the red line is higher than the blue line here doesn't matter. So you look at the energy. And just to belabor the point, yesterday we talked about what the energy was. One of the very first things we did in this review of lectures was to talk about energy signals and energy. Yes, sir.
The square of the difference between the two functions?
Let me be even more precise on the next line. So consider that as just sort of hand waving, pointing out a problem. And so what I want to do is I want to say, supposing I have f of x, and supposing g of x, and I'm going to put a little index in there, n, and I'll explain that in a second. That's going to be a0 over 2 plus the sum k equals 1 to n, ak cosine of kx plus bk sine of kx. Again, I hope I don't disturb you with my notations that x goes to t and so on and so forth. It's all, just it's math at this point. So notice this is not a Fourier series because I've truncated it to n. Okay? So this is a truncated it's a truncated Fourier series. So in principle I can truncate this at 1, 2, 3, 4, 1,027, depending on how much patience I have. So what will happen is somebody will give you money to work on a problem, either a paycheck or a research grant, and you'll just spend the money calculating more and more and more terms of your Fourier series until you run out of dimes. That's not exactly true. But you could, that's a cynical way of looking at it. The better way of looking at it is you'll take the first, you'll take the second, you'll take the third, you'll take the fourth, you'll take the fifth. Then what you'll do is you'll look at the error of the first, the error of the second, the error of the third, the error of the fourth, and the error of the fifth. And when you have a tolerable approximation, when you have a tolerable amount of error left over in your approximation, say it's the old school 5%, 5% is good enough for design work, or the ultra new precision 4 nines or 5 nines, 0.000001 or 3 or 10 to the minus third percent, then you stop your terms. Okay, so the larger the n, the larger the precision of your work, and one of the nice things about technology is one of the frontiers is the precision. So you can view n as an index of our progress as engineering. So let's find the A's and the B's, the A sub k's and the B sub k's, so that, or such that, we minimize the total square deviation. Okay? And the total square deviation is the energy of the error. Okay. So what A's, how can I calculate these A's and B's? Okay, I know how to calculate the A's and B's if n were infinity. Does my answer change if it's truncated?
I shouldn't think so.
Pardon?
I shouldn't think so.
Yeah, but that's not good enough to assure your customer that the bridge isn't going to fall down, or to tell him to get his hand out of the way before he burns it on the rod. Right? So you want a little bit more than gee, I guess so. And since I'm doing the work, you might as well sit back and let me do the work and take the answer to a little bit higher plane. So let's talk about d sub n. And d is for deviation. Okay? And so it's the deviation associated with an nth order series. The nice thing about this weird notation, this t is equal to pi t, this x is equal to 2 pi t. The nice thing about that notation is that I can work with pi's instead of capital T's. It's just a little bit more elegant and maybe cryptic at the same time, mathematics. So I look at at any x, I look at the difference between f and g. So at any x, I look at the difference between f and g, and I square that difference, and then I integrate for all x that I'm interested in. Okay? So that's my total square deviation. Here's my error between the two functions, and here's the energy of the error in my functions. Okay? And so that's equal to and that's a mouthful. So let me break this up for you. I have f of x squared terms. I have f of x squared terms. I've got g sub n squared terms. That guy, and that guy. G sub n squared terms. And then I've got the cross terms. Minus 2 fx gx. And that's sitting out over here. These guys here. So this quadratic of a squared plus a plus b, a minus b quantity squared, a squared minus 2ab minus b squared. And then what I've done is I've reorganized it so that I'm looking at all the different k by k by k. Okay? So that gets me my d sub n, and I want to minimize the overall error of dn relative with respect to the a's and the b's. And that's the same as minimizing term by term because of the way I've, whoops, wrong piece of paper, because of the way I've arranged these. When I say minimization, what am I going to do? Take the derivative. I'm going to take the derivative with respect to the a sub k's and the b sub k's to minimize that. I'm going to check the second derivative. Here's my function, minimize with respect to a certain thing. But since all of these guys are nicely separated in terms of the k's, I just have to go term by term by term. So formally, del dn del ai must equal 0 to minimize, and del 2 dn del ai greater than 0. Okay? So we'll look at term by term. That's a typical term. So I'm going to call that guy delta sub k. All those delta sub k's add up to give me the d sub n's. So there's my delta sub k. So term by term means that I go delta sub k. Ouch. And that's got to equal 0 to minimize. And that's going to equal 2 pi a sub k. Notice I bring down the 2 there. And then this is just linear. So that's going to be a minus 2 times the integral of minus pi to pi, f of x cosine of kx dx. Let's pause there and just remind ourselves where things are coming from. Okay? The capital A's are not the little a's. The capital A's come from the truncated Fourier series. The capital A's come from the truncated Fourier series. F of x is the original function that I care about. So this is relating the capital A sub k of the truncated Fourier series to the function that I care about. Okay? So a big mess, but here's a pretty simple formula. Here's a pretty simple formula. And in fact, it gets even more simple when I solve for a sub k, since I'm interested in what is the k that does this minimum error. And there's my formula for the A's that minimize the energy of that error. The energy between G sub n and F sub n, and F of x. G sub n of x and F sub of x. And the reason it's confusing to you is because this is equal to the A sub k that we had before. Okay? I should have made you say that aloud before I gave you the punchline. Sorry about that. I'm walking all over your joke. But it is a little confusing because you're looking at it and you're saying, wait a minute, I've seen that before. But it's two different things. And that's the beauty of this. A sub k, which we've been calculating, is a truncated Fourier series. It's only good to 7 terms. It's only good to 7 terms. Whereas A sub k was only developed for an infinite number of terms. And the fact that these are the same means that for a finite, therefore, the finite truncated Fourier series gives the best energy fit to the real function or the real signal. Now, it is true that as we increase n, we get better and better and better fits. Absolutely. Thank you. Sorry about that. There's one small little detail here that I didn't do, which is del 2 of this delta k, del a k squared. That's going to equal 2 pi. Come back to here. Take the second derivative of this. That's independent of a sub k. So that's equal to 2 pi. And that's equal to, that's greater than 0. And I think that means that I have a maximum. I'm sorry, minimum. Right? So that's just a little check. Are we getting trapped by our math? We're almost done. That's the punchline. Let's put what we have back in for these guys. Right? We'll put this back in for these guys so that we consider the complete error, d sub n. So all these extra terms here are just written as the infinite Fourier series coefficients, a sub k's and b sub k's. So here's the energy of my signal. Here's the energy of my approximation.
So how is fx in there, but g of x is not?
1 second.
Oh, I guess g of x is converted to the a's.
Exactly right. Exactly right. Here's my n, see?
Yeah.
And in fact, that's great. I'll write the energy of g sub n in there so that we know in the future what we're looking at there. That's the energy of g sub n. And I'll write it again. That's the energy of the truncated Fourier series. Okay? So as the number of terms up here come in, we take that away even more. So the energy of the signal also must be greater than the energy of the truncated signal. Look at that for a second, and you can see that, because the Fourier series of this guy is going to have an infinite number of terms. This is going to have a finite number of terms. The energy of each of those terms is positive. And so this will have 1 trillion terms, and this may only have 3 terms. Then it has 4 terms, and it has 5 terms, and it has 6 terms. As I keep adding terms, I keep whittling away at the energy. So the limit, as n goes to infinity, of d sub n minimum, that goes to 0, and what we've said from a mathematical perspective is that a truncated Fourier series converges in the mean. It converges in the mean, convergence in the mean. Which doesn't mean a whole heck of a lot to me. What does mean a heck of a lot to me from this kind of arcane mathematical proof is that I'm really smart to use a truncated Fourier series. And I'm pretty happy by using a truncated Fourier series. That if I only have time to do 4 terms, the Fourier series from an energy perspective gives me the best 4 terms. Not from other perspectives, but from an energy perspective. And that's a pretty good perspective to be starting with. Okay? If I have time to do 7 terms, I'll do better. And I'll still do the best representation from an energy error perspective by using the Fourier series for those 7 terms. So if I have a chance, if I'm interested in if I only have time to do a certain number of terms, go with the Fourier series. If you're interested in the energy, and very often we are. Okay, so it's kind of a sophisticated proof. It's kind of a sophisticated proof. Mean squared error, Parseval's theorem. I think I just did a homework problem for you. So why you're sitting there saying, why should I care? Well, the punchline is the real reason to care. But from a more practical perspective, I probably just did a homework problem for you. Okay? Which I certainly don't mind doing at all. When you go back to looking at it, you can think more about it. Okay? So this time we finished the Fourier series, and now we'll start in on Fourier transforms. Okay. It's good sometimes to get a little formal proof going. It kind of gets the blood moving in the morning. So Fourier transforms. I'm not going to spend a whole lot of time showing where they come from. I'm going to say that I guess I'm using alpha there. I have a Fourier series representation of x of t, and the alphas give back where the alphas are found by that formula. So you can look at this guy here. Should have left more room. So this integral here takes the time function and it moves that information to a k-space. That's another way what we've looked at, right? We've moved from a time function to a k-space, and this summation here moves from a k space, discretized frequency, to the time space. That's a big leap of interpretation from what we've done with the Fourier series so far, right? But there's nothing really wrong with that. It's just an observation that comes from writing the Fourier series and right next door to the formula for how we calculate alpha sub k. So when we did our Fourier series, we were very utilitarian. How do we do this? Here are some examples, right? Well, now we put the rules together, and we look at them a little bit, and new insight comes out. That I'm starting with x of t, and I move to a frequency representation. It's a discretized. It only occurs at certain integer values, but we have nevertheless moved to a frequency space. A frequency space that we've defined by our period. Okay, if you happen to have a magic function, a periodic function, yeah, that period gives you that, but chances are that's not going to happen. So you're going to be in charge of that period, and so you're going to be in charge of that discretized frequency space. So you can move from time to frequency, and then you can move back from frequency. Once you have this guy here, using this guy here, you can move back to get x of t. And I think I made a mistake here. I think there should be a minus sign there. I think there's a minus sign there. Okay. Pardon?
You also brought the dt.
Oh, I did. Okay. Actually, that's a nice one. I'm glad you brought that up because I'll point out one thing about that. This is an integral across dt, and it's a finite integral across dt, and this is x of t, and this guy here has a k times a t. With the omega naught in there, but it has a k times a t in there. And so I've got t, and t, finite integral, definite integral. The t's vanish. When I do that integration across the limits here, the t vanishes, and I'm left with just the k as the index. Okay? So the integral cancels out all the t dependence, and here the summation, the infinite summation. I'm not sure cancels is the best word. It cancels out all the k dependence. Okay. So that's a complete, nice movement from time to frequency, or from time to k and k to time. The math just happens to show us that. I dribbled in a word a little bit earlier this morning. The word was kernel, Kernal, like a kernel of corn, a gem of something, and always run out of colors. Just for grins, there's my kernel. Okay? That's what I refer to as a kernel, Kernal. And the kernel is really an interesting kernel because it has the product of k and t in it. So both of them are equally important. Both k and t, one is not better than the other when it comes to that exponent. And further, remember what I said about transcendental functions? It better not have, units. In this case, it can have radians. There's a nice debate about whether radians are units or not. I think they are, but doesn't help my case here. I've got omega naught here, which is 1 over time, and I've got time, which cancels. Okay? So I'm moving into reciprocal space. So this is a new way to look at Fourier series. a new look at the Fourier series. If I don't like this discretization, I can let the k, the distance between the k's, get very, 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 very small, in which case this summation becomes an integral. It's sort of that Riemann sum approach again. Fourier series then goes to a Fourier transform, and the Fourier transform pair
off screen.
Good, you can't see my horrible penmanship. d omega dt. Come on, jump down my throat when I make those mistakes. It's fun. So, as you know, x of t and x capital X of omega are a Fourier transform pair. The Fourier transform of x of t, the Fourier transform of x of t, is x of t multiplied by that kernel, slightly different kernel, K-E-R-N-A-L, e to the minus j omega t I omega t dt, integrated over all time so I get all information. X of t can span any instant of time, all instants of time, so I better have my limits of integration cover all the bounds of x of t so that I keep all the information. And what I'm left with after doing that definite integral in time, the time leaves. I'm left only with the omega, and so I have the x of omega. On the other side, to come back, the inverse transform of x of omega, I multiply by e to the I omega t. I integrate across d omega for all frequencies from minus infinity to infinity, and I'm left with x of t. Omega, omega, omega. Omega equals minus infinity to infinity. The omegas vanish from the integral, and I'm left with the t that's in the kernel. Okay? That's the way that works. And so x of t and x capital X of omega are a Fourier transform pair. And I have a continuous representation of time, of the information in time, and I have a continuous representation of the information in omega. So let me back up and repeat that more slowly and with a little bit more emphasis. I have a certain amount of information in this signal. I have the information embedded in the signal. X of omega is the representation of that information in the frequency domain. Same information in the signal, x of t is the representation of that information in the time domain. So it's not that I have x of t and then I have x of omega. No, instead I have the information, and I choose to show that information in the time domain, or I choose to show it in the frequency domain, and I can move back and forth between them by these two integrals. Okay? Which means that I can go round and around and around and around and around all day long. I can go from x of t to x of omega, back to x of t, back to x of omega, because I'm not losing anything because of these, mathematically, because these minus omega, these infinities, and intuitively, because I only have the information of my signal. Okay. Some details on calculations. I think this is the representation that Lottie uses. I think it is. I haven't checked it in a little while, so I could be wrong. My point is that all textbook or many textbooks are used different specifics or different details of the Fourier transform pair. So in this particular case, I've got I have it because I'm working with radians per second and not hertz, omegas instead of f's, instead of new's. Then I've got pi's floating around in my problem, and this pi lives out. I've chosen to lump the correction factor for pi in terms of the inverse Fourier transform instead of the other ones. I've seen it here, and I've seen it broken up between the two. Okay, so that's just that. Similarly, it's a little bit. There's a meaning for why the minus sign is here versus here, but on the other hand, as long as these are the reciprocals of each other, you can mop up the mess if you make it. Okay. I point that out from a practical perspective because you now have several textbooks with Fourier transform tables in them. And your collection will grow, even if it becomes an online collection. And so what you'll want to do when you're doing a problem and you're pulling together information from several different textbooks is you'll want to make sure that your work you're sure in your work about what your Fourier transform pairs are. Okay? It's not a big deal, but you want to get the pi's right and the minus signs right if you're actually doing a calculation that's going to affect, say, some instrumentation that's used in your favorite professor's hip replacement surgery coming up. Okay? Sorry to get personal on that. But you know what I mean. As engineers, we sometimes do design systems, products, devices that where people's life is at stake, and so you should be careful of things like that. Okay. Used to be that electrical engineers didn't so much have to worry about that, but these days, if you look at all the electronics in a car, or an airplane, or a cable car, or biomedical instrumentation, it's just every bit as life vital as a civil engineer designing a balcony or a bridge. So.
The only difference is the book uses the J.
Yeah, as I said, it's J's. I's are so much more fun to write, and certainly the variety is even more fun than that. So again, I'm just hand waving the connection back from the Fourier series to the Fourier transform. I get to do that because this is a review, and you've seen it before. Example. So for a multiplicity of reasons, one of which is that this is an important function, and we care about the actual answer as we go on in many of our discussions to come. I'm going to do the exact same pulse as I did before. I looked at this pulse before, and we got the Fourier series for it. Now I'm going to look at the same pulse, and I'm going to get the Fourier transform of this. Okay. Apologies, I've changed the T1s to capital T's, and I don't have to, and because of these these infinities, I don't have to worry about forcing this guy to be periodic. Okay. Because the infinity's on the integral sign. Same pulse as Fourier series example. Okay. x of omega the function is 1. The height of the pulse is 1, so the function is 1. I don't know if it's more or less confusing if I put that 1 in there. But here's my function 1 and here's my kernel. And I've committed the grave sin of replacing j with I. Oh well. And notice that my minus infinity to infinity has been replaced from minus t over 2 to t over 2 because it's 0 all the way out here and here. Okay. Skipped a couple of steps that I hope you don't stress out about. I've already done this integral, so I can afford to do it a little quicker this time. Integrate this, I pull down an I omega, and I evaluate the resultant integration by function by at t over 2 and minus t over 2. So here's the upper limit, and here's the lower limit evaluation. Okay? And so now I'll take this I, and I'll put it under those two terms there. I'll multiply through by 1 again. A 2 in the numerator, a 2 in the denominator. Now this guy here in brackets becomes the sine of omega capital T over 2. Which means that this equation, this guy here, is twice over omega sine of omega capital T over 2 I've left a little bit of awkward space in there. So what I'll do is I'll fill it up by multiplying through by 1. Capital T over T is 1. And so now you see that I have an omega capital T over 2, and I have an omega over 2, a twice omega T here. So let me, I've got a omega T here, and I've got a 1 there. I'm probably violating some rules of making too many marks on this. So let me go ahead and simplify this a little bit. This is equal to T times the sine of omega capital T over 2 divided by omega capital T over 2. Okay? And then that's equal to capital T, the length of the pulse, the area under the curve of the pulse, multiplied by the sinc function of omega capital T over 2. So here's your sinc function much more explicitly and in continuous frequency space. And we knew this already, right? We knew this from lecture 1 back on Wednesday, where we were doing our favorite Fourier transform pairs, talking through our favorite functions and their Fourier transform pairs. So here's our little slit of light, our little rectangular aperture of light, our little slit of light, and here's the diffraction pattern that comes from that. A real life Fourier transform. Okay. The only thing is here's the details of how to get there, and here's the details of just how fast things move in one space versus the other space. The shorter the t, the bigger the sinc function is there. Okay. quick sketch of that. And I know you're going to cringe at this. So you're going to run home and plot this out much more carefully. I'm probably wrong, but it may be that one of the MATLAB examples whose text you have has this already on it. So here's the plot of the sinc function. And these zeros occur whenever this guy is a 0. So 2 pi over t, 4 pi over t, and so on. 6 pi over t. Not too, quite similar from the discrete case, right? Please note that the zeros are evenly spaced. And that's a consequence of the sign. The roll-off is 1 over t, and that comes from the denominator. The roll-off is 1 over t, and that comes from the denominator. This guy here is capital T, or where the sinc function goes to 1, and that comes from L'Hopital's rule. Got it? Better? Nope. Better. So L'Hopital's rule for the sinc function. Let me just do this. Sine of 0 over 0. Okay? So if I put in omega equals 0 here and omega equals 0 here, I have a sine of 0 over 0. Which one wins? I take d by dx of sine of x divided by d of dx of x. And that's equal to the cosine of x over 1. And then evaluate this at x equals 0, and that equals 1. Multiplied by t, and I get that guy there. Okay? Sine x over x is equal to 1. The width of the pulse in time is capital T. Okay? The width of the pulse in omega, well, that's really tricky. Because the width of it's either infinity or some other number. I'm going to be sloppy about this, so I'm just going to say that I know that it's proportional to 1 over t. You see these guys here? It's 1 over t. So if I just say that it's at this first 0, if I multiply delta t and delta omega, and again, it's really hard to pick a delta omega, then that's going to equal capital T times, let's say, 2 pi over t. That's the first 0. And that's equal to 2 pi. but just as an example. And I pointed out that if you want to do this correctly and more carefully, then you'll want to take the first moment of the time and the first moment of the frequency, and so that's distributions of in the time domain, distributions in the frequency domain, and you'll get a much nicer answer. It's actually the same, almost the same as that. And so this guy here is called the pulse bandwidth product. And that's a really nice concept, the pulse bandwidth product. If I want a shorter pulse in the time domain, I need more frequency. Okay? If I want to be specific about what frequency I'm working at, I need a very, very long time. Okay? If I want a short pulse, that's called a delta function. We've motivated that already. If I want precision and frequency, what's an example of that instrument? Precision and frequency. I want to know a frequency very, very, very well. What's even more common? What's even more common than that? What's even more common than that? We probably all have 3 or 4 of them on ourselves right now. Clock. Right? A frequency standard, a clock. If we know that clock very, 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 very well, we have very, very precise frequency dependence. As an aside, these guys rely very heavily on clocks for synchronization with the cell towers. And there's a fairly major research, and actually I would say there's a fairly major development project going on at many different companies to put an atomic clock on a chip so that you synchronize your cell phone. Every cell phone will have an atomic clock in there, probably in a handful of years. Probably a handful of years. That will allow a tremendous synchronization with the cell towers and frequency assignments that are just preposterously precise so that we can use that precious, precious frequency spectrum that much more carefully. Okay? Very precise frequency sources, high quality factors. And if I wasn't about to run out of time, you could look forward to a great digression on quality factors and where they come up with and the relationship between clocks and bandpass filters and so on. But you might just have to wait till we study noise and the filtering of noise. Okay?